In this video, I will go over how to do sequences and series math problems and the real-life applications of this. Have you ever thought of real-life examples of mathematical sequences? Of course, there exists arithmetic and geometric sequences, but where can you find these and use these in real life? One example is when one person is infected with the virus, and then the next day they infect two people. The next day, those two people infect two more people each, and so on and so forth. Another example is with tables and chairs. If you have a square-shaped table and 4 chairs around it, how many chairs can you fit around 2 joined tables? What about 3 joined tables? This is an example of an arithmetic progression, where adding more tables increases the number of chairs by a certain amount. Another example is a stadium, a circular stadium with seats, with different rows of different numbers of seats, as the first row, the row closest to the center, will have the least number of seats. If the row behind that has, like, say, one more seat, and then the row behind that has one more seat than that, and so on, how many seats are there in total if you only know one of the rows of seats? So these are all examples where arithmetic and geometric progressions are used in real life. So now let's take a look at this arithmetic sequence shown by these 3 diagrams. The first diagram has 3 blocks which make an L shape. The next one also has an L shape, but has increased the height and the length by 1 block. So this one has 1, 2, 3, 4, 5 blocks, 2 more than diagram 1. The third one has 1, 2, 3, 4, 5, 6, 7 blocks, also 2 more than diagram 2. This one has also increased 1 in the height and the length from diagram 2. So here we can clearly see each diagram has 2 more than the previous diagram, with the first diagram having 3. So it goes 3, 5, 7, then the next one, diagram 4, would have 9 blocks, and then diagram 5 would have 11, and diagram 6 would have 13 blocks, and so on and so forth. Here we can see that this is an arithmetic sequence, because each diagram has the same number of blocks more than the previous. It's always 2 more blocks than the previous diagram. An exercise for the viewer can be to find the number of blocks in the 30th diagram. Another exercise could be to find the number of the diagram that has 53 blocks. Here we can see that there are red blocks and yellow blocks. So let's count the number of red and yellow blocks and the number of total blocks in each diagram. For the red blocks, there's 1 in the first one, 3 in the second one, 5 in the third one, and 7 in the fourth one. So here the difference between each 2 terms, each 2 diagrams, is always 2 red blocks. So the number of red blocks can be an arithmetic sequence. Now let's look at the yellow blocks. There's 0 in the first one, 2 in the second one, 8 in the third one, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 yellow blocks in the fourth one. Now here the difference between the first 2 elements, the first 2 terms, has 2 blocks, 2 yellow blocks. The difference between the next 2 ones have 6, and the difference between the third and the fourth one have 10. So since those are not the same, this cannot be an arithmetic sequence. Now let's count the total number of blocks. 1 in the first one, 5 in the second one, 13 in the third one, and we counted 7 red blocks and 18 yellow blocks in the fourth one, so that's 25. So the differences there are not the same either. So the number of yellow blocks are not an arithmetic sequence, and the total number of blocks are not an arithmetic sequence either. Only the number of red blocks are, because remember, it's about the same difference between 2 adjacent diagrams. From these examples, we can clearly see that there are many places around you where you can find arithmetic sequences. I hope you enjoyed this video, and thank you for watching.